Well, good morning. I think we're now live, at least I hope so, and I can see we've got a good number of participants in the session. So I'm going to start us off. I'm Robert Massey. I'm Deputy Executive Director of the Royal Astronomical Society, and as you know, we're hosting the webinar this morning. It gives us enormous pleasure to be doing that. This is, in case you've missed it, it's 2020 is our bicentenary year, a year we didn't quite expect to go in the way it did. And it's very appropriate that we're hosting this briefing because our founding president, William Herschel, was our president briefly back in 1820. He was not just famous for discoveries of planets and comets and nebulae, but also was someone who attempted to make a map of the galaxy we live in. I doubt he could have imagined the scope and the accuracy, the extraordinary scope and accuracy of the Gaia catalogue, which is something that's set to underpin astronomy, I think, for decades to come, and which we're here to find out more about this morning. And now that the end of the pandemic is in sight, we obviously look forward to welcoming you all back to our premises at Burlington House in London, perhaps in the autumn of next year. And certainly that'll be a huge pleasure for all of us. But I would remind you as well that we are running sessions, nonetheless, scientific sessions like this one, and also our regular programme meetings if you're able to join those. And we'd be delighted to see you at those too. Now, the housekeeping stuff is shorter than usual, as one of my colleagues pointed out. I don't have to give you fire safety instructions, but I do want to give you some advice on, if you haven't joined one of these sessions, on the best way to take part. Our panelists, we will see their video, we will hear their audio, we will see their slides. If you're an attendee and you have the link and are joining through that route, then you don't see most of that. You see most of them, but you won't have your own video or audio on. So what we'll be doing is we'll be taking questions using the Q&A box, which you should see at the bottom of your screen in Zoom. And we will moderate those, myself and my colleagues. Some of them will answer live. If they're things relating to the session, we can try and answer them privately. We'll read them out after the different presentations and invite the speakers to answer. Do remember too, this is an embargoed session and the data from Gaia and ESA are not live until 11 o'clock. So please don't comment on them until social media until then, just to respect that embargo. If you're here as a member of the media, I know the media session proper starts at 10:30, but if you are here as a member of the media, please edit your Zoom names so that we can see that you're a journalist, because in the second part of the session, we will try, depending on numbers, to allow oral questions. It's not a promise, but we'll see what we can do. Other than that, though, it's my pleasure to hand over to Nick Wharton, who will be chairing the first session. So over to you, Nick.
Right, okay, thanks very much, Robert. I'll just share my screen and get this to run there. Okay, welcome everyone. Good morning. This is release day for Gaia Early Data release number 3 in the sequence, and I'm Nick Wharton at the Institute of Astronomy in Cambridge and a member of the ESA Gaia science team. I would just like to welcome you all to basically the last couple of hours before Gaia Data Release 3, which will be released and be available at noon Central European time, so 11 o'clock in the UK. Here's the banner logo. This really truly is representing the next milestone or the next step in astrophysics. What is Gaia Early Data Release 3? Well, we're going to hear about that in the upcoming presentations. Briefly, this is releasing 1.8 billion updated positions, brightnesses, and parallaxes. So it's building upon Data Release 2, but with significant improvements in the proper motions, for instance, factors of 2 almost in the proper motions, and improvements in the parallaxes. In the next few minutes, you're going to hear about the UK role in the release of the data release. The UK team involves groups in Cambridge, Edinburgh, Leicester, and UCL in London. And the presentations you're going to hear from Nick Rao talking about the astrometric data sets, David Evans, the photometry, and George Seabrook, the radial velocity data. So these will give detailed presentations of the contents of the archive data set. Data release 3 is going to enable significant new scientific insight. So we've got presentations from about 10 o'clock that are going to describe some of the key results from the performance verification papers that are also going to be released today with the data release. The 3 papers that we're going to talk about, Francesca De Angeli is going to talk about the results from the LMC and the SMC paper. The first direct measurement of the acceleration of the solar system results are going to be described by Floor van Leeuwen, and Georgia Busso is going to, in the press release section at 10:30, describe the 100% solar neighborhood nearby catalogue of objects from the EDR3 release. And I think with that, I will just point out that the data will be available from the normal early data release 3, the normal ESA Gaia archive page. From 11 o'clock GMT, you will see that the new source table is available, the EDR3 source tables. There is a full set of information also on the ESA Gaia Cosmos web pages under early data release 3. I do encourage everyone to look at those. There's some very interesting background, also a lot of some interesting stories around EDR3, and then the links to the DPAC consortium, and of course Gaia in the UK. And with that, I will hand over to my colleague Nick Rao from Edinburgh, who's going to talk about the astrometric data.
Okay, thanks, Nick. I think you just need to stop sharing the screen.
Yeah, there we go.
Right. Okay, can you see my slides okay?
Yes.
Yeah, okay, there we go. Yeah, thanks, Nick. So I'm Nick Rowell at the Institute for Astronomy in Edinburgh. I'm a member of the UK Gaia data processing team. And I'm going to tell you about the astrometric data that's released as part of EDR3. But first, some context. So distances to objects in the universe are notoriously difficult for astronomers to measure. There's numerous ways that have been devised to do it, but really the gold standard is the method of trigonometric parallaxes that's depicted on the top right of the slide here. And this is where we use the Earth's orbit around the sun to provide a very long baseline for triangulating the positions of nearby stars. This is in principle how it's done. The technical details are a lot trickier, but ultimately it relies on making very accurate measurements of the positions of stars over time, which is the discipline that's known as astrometry. So astrometry also allows us to measure positions and angular motions of stars. And the reason this is important is that these quantities reveal the fundamental nature of individual stars, but also populations of stars and the galaxy as a whole. So Gaia is principally an astrometric mission that's been tasked with measuring astrometry for a very large number of stars in the Milky Way and some nearby galaxies. The satellite itself is not on Earth, it's in deep space orbiting the sun in a region known as the second Lagrange point that turns out to be very favorable for making the kind of very accurate position measurements that we rely on. It uses 2 telescopes and continuously spins to scan the sky. So Gaia EDR3, the astrometric data, is based on around 34 months of observations taken by Gaia. In total, this amounts to around 700 billion individual CCD observations of stars. On average, each star has been observed around 280 times, although this varies very strongly with sky position. So in terms of raw data, this is around 50% more than what went into the second data release. And this immediately gives us an increase in the accuracy on all of the astrometric quantities that we measure. The increased time span also gives an additional boost to the proper motions. And these reduces the random errors on the astrometry, but also Major step forwards with EDR3 are some significant improvements in the basic instrument modeling and calibration, which reduces the systematic errors present in the catalogue. One example of this is on the right of this slide, where we show the improvement in the point spread function modeling that's been brought in with EDR3. Gaia ultimately measures positions of stars by point spread function fitting. So the astrometric method involves using the measured positions to simultaneously solve the astrometry, satellite attitude, and instrument geometry over the full 34 months. The full details of all of this and what's contained in these slides are presented in the astrometry paper that accompanies the data release. So looking at some of the numbers, EDR3 contains full astrometric data, that's positions, proper-motions, and parallaxes, for nearly 1.5 billion sources in total. So of these, around 900 million that don't have an accurate color measurement, these also solve for an additional color parameter in the astrometric solution that's designed to reduce the effects of chromaticity, which is the tendency for the instruments to measure red and blue stars slightly differently. What's depicted on the right of the slide here is a histogram of the number of sources with different types of astrometric solutions. So in as a function of the Gaia G-band magnitude from the bright end at around 2 or 3 down to the faint end at around 21. So in blue are all of the sources with 5 parameter astrometry. In green are the sources that have been fitted with an additional 6th color parameter. And in red are around another 344 million stars for which only the positions could be solved, mostly faint objects. So a very important subset of the astrometric catalogue are the quasars. There's about 1.6 million included in EDR3 that have 5 parameter astrometry. Quasars are very distant objects for which the intrinsic proper motion and parallax can be assumed to be 0, and these provide a very useful set of data for making statistical assessments of the astrometric solutions. They're also used to define the reference system in which the Gaia astrometry is defined. So looking at the uncertainties that have been reached with EDR3, so we'll focus on the parallax uncertainty, but the other astrometric quantities have very similar properties. So the median uncertainty on the parallax for a 15th magnitude star is around 0.027 milliarc seconds, or mass. Mass is a very small angle unit that we use a lot in Gaia. It's equivalent to around 1/billionth of a circle. So this uncertainty on the parallax is roughly equivalent to the angular width of a pound coin viewed from around 200,000 kilometers. So this uncertainty is about a factor 0.7, smaller than in data release 2. For the proper motions, the uncertainties are about a factor 0.44 times a DR2 value. So these have come down a lot, and they've come down by larger amounts than what we expect purely from the increase in the quantity of the raw data, and this is due to the improvements in the instrument modeling. These uncertainties vary strongly with both the magnitude of the source and position on the sky, which we'll just have a look at. So the uncertainty on the parallax and the astrometric quantities shows a very strong dependency on the magnitude of the sources. What's depicted here is the uncertainty on the parallax as a function of Gaia's G-band magnitude. You can see a very strong trend here. This splits naturally into a couple of broad regimes. Down at the faint end here, we're limited by photon noise, and really the best thing we can do to reduce the errors in future in this range is to gather more data. At the bright end, on the other hand, we are in the calibration limited regime, where the best thing we can do in future is to improve the instrument modeling. The uncertainties on the astrometry also vary greatly across the sky due to various geometric factors that originate in the particular scanning law that Gaia follows. So on the left, this shows a sky projection in equatorial coordinates of the median parallax uncertainty. What you can see is a broad sweep across the ecliptic plane here, where the parallax uncertainty is slightly larger and it's smaller towards the ecliptic poles. And this roughly mirrors the scanning pattern of Gaia, which is depicted on the right here. So the plot on the right shows the same projection, but now this is the number of times roughly that each region of the sky has been scanned so far in EDR3. You can see this very characteristic sort of spirograph pattern that over time will be filled in later data releases. Another important quantity is the parallax bias, or the 0-point offset. In EDR3, this is now at around negative 0.017 mass. This is roughly the parallax that Gaia would measure for an object that has a 0 intrinsic parallax. And this is something that's estimated from the quasars. So this is reduced overall from the second data release, where it was around negative 0.03 mass. We hope to bring this down further in future. It depends strongly on source color, magnitude, and sky position in complex ways. Suggested corrections that astronomers might want to apply are provided as part of the EDR3 release in the papers. So as well as the astrometric raw data, well, the astrometric quantities, we provide various statistics that astronomers can use in assessing the quality and reliability of the astrometric data for each source. And these are described in detail in the papers that accompany EDR3. So just looking ahead a bit to future data releases, future Gaia astrometric data will benefit from increased quantity of observations and also the increased time range, and some further substantial improvements that are still to come in the core instrument modeling, which are mainly carried out by the UK Gaia team. The next update of the astrometric data will be in data release 4, which is still to be determined, and substantial work on this is already underway right now. And I'll just finish with the acknowledgements for the papers that have been released today that are from which the data and figures in these slides came from. And thanks. I'll pass back to Nick.
Right. Thanks very much, Nick. We've had a question come in which is asking about the uncertainties on the parallax. I think this is a good one to answer quickly. Basically, it's Tom Marsh saying that the parallax is improved by as much as 0.71, which you might expect 2 times more data when we've only got 50% more data. I mean, basically, this is around improving the systematics as well as just the extra data.
Yeah, exactly. So I think we'd expect around 0.8 improvement from purely the increase in raw data. The extra factor comes from the improvements in the instrument calibrations. And yeah, there's more to come in future in that regard as well.
Yeah, it's beating down some of the systematics, and to everyone there was a lot of information about how those improvements have been made in the release documentation that will be visible very shortly. Thank you, Nick. And let's move on quickly to David Wynne Evans from the University of Cambridge, who's going to describe the photometric data set. Over to you, David.
Okay. Hopefully you can see my slides now, or appearing to.
Yep, that's all good.
Okay, so I'm going to be talking about the photometric content of the catalogue. EDR3 has about 100 million more sources in comparison with DR2. So this means that the G band has about 1.8 billion sources, and the BP and RP photometry has about 1.5 billion sources. This is where we get the color from the BP and the RP. Of course, in this short presentation, I won't be able to say much, but if you want more details, go to the main photometric paper that's released today in ANA. That was written by Marco Riello and the rest of the team. EDR3 is early data release 3. This is because the original plan was that DR3, which will be released in the first half of 2022, would have contained the photometry and the astrometry and the rest of the data. And because it would be 4 years since the DR2, we thought that since the photometry and astrometry is available a lot earlier, because of the way that we process the data, it was better to actually release this data as an intermediate data set. So when DR3 comes out, it'll contain more photometric content. In particular, there'll be 300 million low-resolution spectra. There will also be photometry and spectra for thousands of solar system objects. In these cases, these are mean spectra and mean photometry values. But there will also be epoch photometry for about 7 million variables, detected variables, and also around 5 degrees around the Andromeda galaxy, there will be epoch photometry for all sources. So the improvements in the photometry in EDR3 are for the G-band, as Nick has described, that the LSF and the PSF determination has improved, and this then improves the fluxes and the positions that we get from the fits that are done to that data. And this then, of course, yields better photometry and astrometry, of course. And then there are fewer systematics, such as magnitude terms, which are reduced. There is also better handling of the saturation and the treatment of the background. For the BP and RP photometry, the background calibration has improved for that, and I'll show some results in a few more slides. Crowding evaluation has also been implemented, and this is important because the BP and RP detectors have got larger windows, and there's a larger chance that a secondary source will be inside that, and that will then we now have a metric that can indicate if this has occurred. The calibration model for the photometry has improved. We've altered the color model that's used. We've added flux loss terms, and there's better handling of when the calibrations are non-optimal as well. Not only do we release the photometry itself, but of course we have to release what the passbands are that are appropriate for these for the photometry, and we stress that the photometric system is different and independent to the one that was in DR2. This means that direct comparisons of the photometry between EDR3 and DR2 values are not useful. It's not only that they are on different systems. Of course, we've done significant improvements in the photometry, so most of the differences that you'll find between the two catalogues will be due to systematic effects in DR2. Okay, so in terms of the precisions that we've got, there's been a progressive improvement with each data release. And this is shown on the right and on the top for the G-band. Because we've had 3 data releases with the G-band, you can see that there's a progressive improvement in the accuracies as a function of magnitude. And in particular, at the bright end, you can see that the effects of things like saturation have considerably improved. Then the bottom 2 plots show the effects, similar sorts of effects for BP and RP, and for the 2 data releases we've had for that data. Now, the results that I'm showing here have taken into account the different number of observations that were available for the data releases, and for EDR3 itself, the accuracies that we'll get will be even better than the ones shown here due to the larger number of observations per source. So it's not just the precisions that have improved. We've also got far fewer systematic features in EDR3 than in DR2. In DR2, we had various patterns that could be seen in the data as a function of sky position, for example, caused by the scanning and issues with the calibrations between the scans. And as you can see that in EDR3, these patterns have gone. Also, if you look at the flux excess factor on the bottom plot, on the left-hand one, you can see the effect of zodiacal light. This is the very faint yellow S feature that's going through the galactic plane, through the galactic center. And in EDR3, this feature is not present at all, showing that the background handling has been a lot better. And also, we've improved the handling in the galactic plane and in crowded regions. There are a couple of known photometric issues in the catalogue. These were discovered and the curation of data, so they weren't able to be corrected or allowed for. So at the very faint end, the BP flux has been overestimated and sources appear to be too blue. Now, this is close to the detection limit in BP. So one of the things that can be done is you can filter out sources with a BP fainter than around 20.3. Now, if you don't want to do that, an alternative is that for a color, you can then use G minus RP to study very faint red sources rather than using BP minus G or BP minus RP. Additionally, the photometry for the sources with 6-parameter astrometry, this was mentioned by Nick in the previous presentation. These are sources that have had their PSF selected from a default color, and this can lead to a systematic effect of around 2.5% for the reddest sources. So a correction should be applied for these, and when you apply this correction, you can see that the effect gets corrected out nicely. Formulae and ADQL and Python recipes for this correction is available in the main photometry paper. So a quick note about the flux excess factor. It's recommended that you use the corrected form of the BPRP flux excess factor, C star. Formulae for this and ADQL Python recipes are available for this in the paper. The reason for doing this is that it just makes it more convenient to use. We get for well-separated sources, single sources, you get the distribution around 0. Now, flux excess can indicate issues with crowding or background subtraction, and the plot on the left shows this. So if there is a blend occurring for BP and RP, this is indicated with the yellow and orange colors. You can see that the flux excess is higher than for other sources. But this flux excess factor can also contain astrophysical information, as you can see in the plots on the right-hand side, where galaxies, quasars, variable stars, and planetary nebulae can also intrinsically have higher flux excess values. So it's important that you don't specifically filter out on flux excess if you are studying these types of objects. And we change the emphasis now for the flux excess factor, that it's not a quality metric, but it's more a consistency metric. So it does depend on the application you have for the data. So although Gaia is primarily an astrometric instrument, the real power comes from combining this with photometry and other data from the satellite. Now, I don't have to remind this particular audience that the combination of magnitude, color, and parallax gives the well-known HR diagram, but with the addition of the Rouvet statistic, we get yet another dimension, and this was shown in this plot here from Vasily Belukharov's paper. And this, the Rouvet statistics shows the deviation from the standard single star astrometric model. And of course, if it's deviating, it indicates a form of probably of binarity. And in the plot here, you can see that multiple star systems are slightly higher than the main sequence, which is what we expect. And then between the main sequence and the white dwarfs, you see binary sources which contain white dwarfs and M dwarfs. Okay, the general conclusions from the that are in the EDR3 paper, which is out today, as I said, in ANA, is that there are no significant G magnitude terms at the 1 millimagnitude per magnitude level. For very blue sources, there is an indication of a differential color term at around the 1% level. Single passbands are sufficient to describe the data and to achieve 1% accuracy. This increases to about 2% for the 4,000 or so sources that are bright and very blue. We have a better background estimation for all three passbands, and also a better consistency between these three. The saturation handling has improved in the G band, and we also overall have a better filtering of bad data. So this means that you don't see the cat scratches, as they were called, in the sky distributions, as was in DR2. Also, the stability of the photometric system has improved, so there are no more discontinuities at G equals 13 and 16th magnitude, and overall we have improved models. Okay, and that's it. Thank you.
Okay, thanks very much, David. I think that's showing some significant improvements in the photometry, and that coupled with the astrometry as a significant improvements in the data that's going out in well, just over an hour or so from now. Let's move now to George Seabrook at Mullard Space Science Laboratory, UCL. He's going to talk a little bit about the radial velocity spectrographic data. There's not a lot of change in the RVS release, but there are a few updates, and George is going to, in EDR3, and George is going to tell us what they are. So over to you, George.
Yeah, thanks very much, Nick. So can you see my
all of that? That's good.
Yeah, okay, great. So yeah, thank you very much. So it's my pleasure this morning to present the radial velocity data in Gaia's early data release. So yeah, as Nick said, my name is George Seabrook. I'm based at the Mullard Space Science Laboratory, which is part of University College London. I'm the deputy lead of Gaia's Data Processing and Analysis Consortium Coordination Unit 6, which is responsible for the spectroscopic processing. And I'm giving this talk on behalf of all these lovely people shown here. So on the left is the MSSL, the Mullard Space Science Laboratory Gaia team, and on the right it's the CE6 team made up of scientists and software engineers from around Europe. So as the name suggests, Gaia's radio velocity spectrometer is measuring the radio velocities, so the speed of stars along their line of sight between us and them. It does that by dispersing the starlight into a spectrum, and here is shown a typical spectrum. We're showing the plot here shows brightness plotted against wavelength, and the wavelength is centered on the so-called calcium triplet lines. So these are the three strongest absorption lines indicated with a CA there, and the wavelength range is centered around those lines. So we measure the radio velocity by comparing the observed spectrum to a model spectrum, and if the observed spectrum has shifted, so the Doppler effect can move the lines. If those lines move away, if they move to the red, according to the model, then that indicates the star is moving away from us. And if the lines move towards the blue end of the spectrum, then that's indicating the star is moving towards us. So here's some examples of the beautiful spectra that Gaia's radio velocity spectrometer is producing, or RVS for short. So I'll refer to RVS spectra as distinct from the low resolution spectra that David mentioned in his talk just now. So the changing morphology in the RVS spectra goes from the coolest star in the top left all the way down to the hottest star in the bottom right. So Gaia's second data release, which came out back in April 2018, contained more than 7 million sources with radio velocities. So the data we're presenting today contains the same Gaia DR2 radio velocity values as was released back in 2018. So that's an important point to note. But the difference is that we've removed nearly 15,000 of those, so just 0.2% of that data. So this presentation is going to be about the reasons for removing those radio velocities. Some of them were removed because they were found to be spurious, and some sources could not be matched between DR2 and EDR3, but the radio velocities were good, but because the sources weren't there, the radio velocities couldn't be either. So some of the exciting science that can be done with radio velocities and the astrometry in Gaia is looking for so-called hypervelocity stars. So these are stars that are so fast, moving so quickly that they can escape the gravitational potential of our galaxy. So the theory is that they've been sped up by gravitational interaction with the supermassive black hole in the galactic center. But as the RCS impression shows on the left, they could also be coming into the Milky Way from other galaxies. So this is important because it gives us information on the mass of our own galaxy and past interactions with other galaxies. So as I say, we can find hypervelocity stars by combining radio velocities with astrometry to get the three-dimensional motions of these stars. So the radio velocities are important here, but unfortunately, some of them were wrong in the last data release, Gaia DR2. So what went wrong? So looking at particularly one of the most promising candidate stars for being a hypervelocity star is the one shown in the left plot here. It was measured to be speeding towards us at an eye-watering 600 kilometers per second. But Buber et al. Used ground-based telescopes to measure this same star and found that it was actually moving at a far more pedestrian 60 kilometers per second towards us. So this spurious radio velocity was due to the chance alignment between spectra blended together. And this is illustrated in the plot on the left. So this is a sky view of the source in question that was thought to be moving at 600 kilometers per second. That's in the blue square. And it has a source, another star close to it with the triangle. And the orange lines are Gaia's scans through that part of the sky. And you see that the scans go through the two stars there. So Gaia's radio velocity spectrometer, the RVS spectra are dispersed along these orange lines. So you can see that the two spectra will actually blend. And so what happened was that the spectra were actually contaminated, causing this spurious radio velocity. So Buber and his collaborators published a list of 70,000 stars, which may have been affected by a similar issue to this. So the paper that I'm working on has found that that less than 4,000 in this list are actually spurious or considered at risk. So these have been excluded from the data which are coming live in about an hour. The other reason for sources not to have radio velocities in EDR3, whereas they did in DR2, is that the source themselves could not be matched between DR2 and EDR3. So this is due to being close pair binaries. So in this case, the DR2 astrometry was based on one of the components in the binary, but the EDR3 astrometry was actually based on the other. And so when you try to cross-match DR2 to EDR3, to be able to match the radio velocities to the EDR3 sources, which are in the database, a match couldn't be found. So this happens for nearly 11,000 DR2 sources, which have radio velocities. So these sources are not in Gaia EDR3, and so neither are their radio velocities. So the plot on the top here is a logarithmic scale on the y-axis showing the number of sources against the EDR3G magnitude. So this is approximately the visual magnitude. So it shows that this issue removes the majority of sources at the bright end, shown in the red line here, coinciding with the black line at the bright end, around so between 2 and 4 magnitude. The plot below shows that these sources, when you plot them in their galactic coordinates, actually show up particular scans, scans that Gaia was making in that part of the sky, and so the issue may relate to that. So this is a summary plot of the radio velocities in Gaia EDR3. So these are plotted in a histogram of the radio velocity distribution. The Gaia radio velocities that are about to be released are the Gaia EDR3 ones in red and the Gaia DR2 ones in blue. So you can see that most of the very high velocity stars or the hypervelocity candidates that form a tail out to 1,000 kilometers per second have been removed in EDR3, including the star that I mentioned earlier. So there's still more than 7 million sources with radio velocities in EDR3. Remember, these are the same values as were in DR2. It's just that they've been cleaned, and the nearly 15,000 have been removed. So the 10,000. So the vast majority of these have been removed due to an inconsistency with the Gaia EDR3 astrometry, and only around 4,000 have been removed due to being spurious. So the details of those will be in my paper to come. So I'd like to finish now just with a summary of what's in the radio velocity data that's in DR2 and EDR3, and compare to what will be in Gaia EDR3 in the future. So this is expected, the full data release of the third data release from Gaia is expected in 2022. So the V magnitude for a typical solar type star, we're going 2 magnitudes fainter in DR2, and this will give us an increase in the number of stars with radio velocities from 7 million, which are available now, up to about 30 million, so more than a factor of 4. So a crucial difference between DR2 and DR3 is that we are deblending overlapping RBS spectra. So the issue in DR2 with the hypervelocity candidate was that we were not deblending, and we got a spurious velocity. So now we are deblending, and we now get the correct radio velocity for that star, but that's in DR3. And I should say that the 30 million radio velocities in DR3 have been produced and are being validated within DPAC at the moment. So the data duration, we get an extra year's worth of data looking forward to DR3. This increases the median number of transits, and this gives us the possibility to fit binary orbits. So the radio velocities are being used to try to fit binary orbits to binary systems. These weren't available in DR2, but will be available in DR3. Also, the spectra from which the radio velocities were derived while being produced internally were not published in DR2, but they will be published in DR3 of the order millions of FGK type stars. And also the astrophysical parameters that have been derived from the RBS spectra were not available in DR2, but will be published alongside the spectra from which they've been derived in DR3. So this table shows that the main excitement and new data products from Gaia's radio velocity spectrometer are being released in the full data release 3 in 2022. But in the meantime, we've updated and cleaned the radio velocities from DR2 to be published today in EDR3. So we're looking forward to the science that's going to be done with those and all the other data products. So thanks very much.
That's great. Thanks very much, George. Some interesting shows you some of the detail and the sort of care that we're going through with the data releases. There was a question, but I think it'll take a little bit of time to answer. So I'm going to suggest that we that George answers that in the chat, in the Q&A chat there.
Okay, sure.
It's somebody spotting something interesting in the radial velocity distributions. I think now, though, we'll move on to the presentations of a couple of science papers, and I'll hand over to my colleague Jerry Gilmore, Professor Jerry Gilmore at the Institute of Astronomy, to introduce the next session. So hand over to you, Jerry.
Thanks, Nick. Hello, everybody. This is it's just over 20 years ago that a few of us presented the Gaia mission for approval to ESA. Happily a successful presentation. But a key part of that presentation was our realization that the volume and range of science capable of coming from the Gaia data is so vast that it would be just silly to try and do it internally. And so we proposed that, in fact, we would do what we're doing and make all the data available to the community. But before it can be released, a bit of sanity checking has to be done, and this leads to a small number of performance verification papers. They're a very small fraction. As you probably know, there are more than 1,500 science papers a year coming out of Gaia. It's the most successful space mission of all time, comfortably. But the illustrative science performance verification papers, we're now going to go through 3 of them. We'll start with Francesca De Angeli, who leads the Data Processing Centre in Cambridge, who's going to talk about the Magellanic Clouds and Gaia's view of them. So over to you, Francesca.
Thank you, Jerry. Yes. So my name is Francesca De Angeli, and I have been involved in the Gaia project since 2005, always as part of the group that is responsible for the processing and preparation of the photometric and low resolution spectroscopic data. I will, as Jerry introduced already, I will now show you some of the results included in one of the papers that accompany the data release. This is one of the papers that are called performance verification papers, and that have really the goal of challenging the performances of the Gaia data in a number of more or less obvious science cases, with the aim of really testing and probing the quality of the data. The one I will be focusing on studies the structure and the kinematics of the large and small Magellanic Clouds. The clouds, well, don't probably need much of an introduction, but they are 2 satellite galaxies of the Milky Way, and they are located at about 50 and 62 kiloparsec from Earth. Because of their distance and density, the Magellanic Clouds constitute a challenge for the Gaia astrometric and photometric data, and are therefore an excellent case study to test the quality and properties of the data. The analysis is based on 2 data sets, one for each cloud, selected first of all to be in a region in the sky within a given apparent distance from the centers of the large and small Magellanic Clouds. Literature values were used for the coordinates of the centers, and to have also proper motions that are compatible with the typical proper motion of the clouds, and this was estimated from the Gaia data itself. A parallax filter is also applied to exclude objects that are not compatible with being distant enough to be part of the 2 satellite galaxies, and also well, this of course has the final goal of cleaning the data set from contamination from the Milky Way. This provides us with two basic samples of 11 million objects for the Large Magellanic Cloud and 4.7 million objects for the Small Magellanic Cloud. And the two plots in this slide show their distribution in the sky in the orthographic projection adopted in the paper. Thanks to the availability in Gaia EDR3 of a reliable and homogeneous photometry in 3 bands for all the objects in this selection, it has been possible to position them in a color magnitude diagram, which you can see in the left plot, and create further subsets from different sequences or regions in the color and magnitude distribution. In these plots, in the left you can see the color magnitude diagram for the LMC showing the polygons that were defining these selection criteria, and on the right the distribution of the various subsets. These subsets are defined, well, 3 subsets are defined along the main sequence. Then there is a subset for the blue loop stars, one for RR Lyrae, one for the asymptotic branch, asymptotic giant branch, red giant branch, and red clump, finally. All of them are quite well populated, as you can see from the right panels. Even though this is quite a rough selection, not even taking into account reddening effects, for instance, in a first approximation, the various subsets can be seen as covering different ranges in age. Now, there was no attempt at estimating the age for each single object, but accurately, but using a simulation, a simple simulation based on our constant star formation rate, given age metallicity relation in the library of models, one can give a first order estimate of the distribution in age of each of the subsets. This is what the result of this is, what is shown in the main panel in the slide. And as you can see, the youngest populations, young 1 covers ages smaller than 50 million years, followed by the other 2 young subsets, the blue loop stars and the AGB, while red clump and RGB stars include the older objects in the data set. Naturally, because this is part of our validation activities, well, it is natural to look at, to compare, let's say, performances of EDR3 with respect to previous releases, to DR2 in particular. It has been mentioned before, but I would like to stress here again that this can only be done meaningfully when looking at statistically significant data sets. It makes very little sense to compare results on an object-by-object basis. This is mainly because of the different observations that could have been associated to a specific object as defined by its source ID, but also because the evolution of the strategies used to process and calibrate the data is so big that it really each data release should be seen as a completely new catalog. What we can see, however, what we can see with the data set that we have at hand for the 2 clouds is that some features that had been noticed in the DR2 data as due to systematic effects are not present or are much reduced in EDR3. The plots in this slide show, for instance, the case of the checkhead pattern that was visible in the DR2 astrometric measurements that are in the top panels in the slide for parallax and 2 proper motions components, which is very, very much reduced in the EDR3 data, which is shown in the bottom row plot. Likewise, we can do a similar comparison for the photometry. So in DR2, the distribution of the photometric flux excess factor, which is in the left plot here in the region near the Magellanic Clouds, showed quite clearly that the BP and IP data in crowded regions was suffering from systematics due to a mostly uncalibrated background and contamination from nearby sources. In EDR3, instead shown here in the right panel, the situation is much improved, and the BPIP photometry is generally much more consistent with the G-band photometry. And this is mostly thanks to higher resolution background calibration, and further improvements can be expected in future releases when we will try also to separate out the contamination in the BP and IP low resolution spectra due to very close objects. Well, this was mentioned already in David's talk before. There are also some stripes that are barely visible in the left plot, which are probably linked to satellite scans. These are not visible at all in the EDR3 plot on the right. Well, it is unlikely that these were connected to background issues, but could have been due to other systematics still present in the photometry, in photometric data, which are now calibrated out. One of the goals of the paper is the study of the kinematics of the large Magellanic Cloud. This analysis is mostly focused on the large Magellanic Cloud, which has a better defined structure with a clear disk that can be meaningfully modeled even with a simple model, while the SMC has a more irregular structure. The strategy adopted in the paper is to fit the proper motions of the Large Magellanic Cloud dataset with a model representing a flat rotating disk with an average radial velocity equal to 0 and with a tangential velocity in the disk that is a function of the distance from the center of the cluster. This center is what is known as the rotational center of the LNC. It is an important ingredient in the model, and different models are solved for in the paper. Not all of them fit the rotational center. Some of them assume, well, use values that are available from the literature, but some of them do attempt at solving also for the rotational center. And this is what is shown in the plot in this slide. So the colored crosses are the results that are obtained from this simple model. When fitted, the value obtained is somewhat closer to the photometric center, which is marked in the plot with FOT, with respect to values obtained from H1 studies, for instance, and from HST proper motions for the rotational center, which are towards the right top corner of the plot. The results do not change significantly when filtered data in the innermost 1, 2, and 3 degrees, where objects show significant non-circular motion, which is probably not well captured by the simple model adopted here. And this is also combined with a large statistical weight due to the high density in the inner regions. So it seems to be quite a robust result with respect to these, at least. If anything, the rotational center seemed to move even closer to the photometric center. Other parameters that are fitted in the model are the bulk velocities in all directions, the inclination of the disk and the orientation of the disk, as well as the parameters describing the rotation curve. Once all these main parameters have been estimated, it is possible to create maps of the tangential and radial velocities and the velocity dispersion as well for each of the evolutionary phases. These maps, I believe, are the first of their kind ever obtained for an extragalactic disk with the separation of the evolutionary phases. I'll show here only maps for a young and an old subset. They all present a somewhat noisy pattern, which might be linked to the residual checkered pattern seen in the astrometric data, which is not completely removed yet, but also all of them show clear variations occurring at larger angular scales that are likely to reflect truly perturbed kinematics in the spiral arms and bar. The younger population here shown in the left plots present larger tangential motion as a signature of asymmetric drift, while both young and old populations show lower tangential velocities in a region apparently aligned with the bar. In fact, some pixels along the bar have negative velocity, which could indicate counter-rotation, but could also be a result of incorrect assumption in the model in those perturbed regions of the disk. The radial velocities map, which are shown in the bottom two plot, also show stronger motion for the younger population. The overall radial velocity is negative in the inner region, indicating inward motion toward the center of the LMC, although this depends quite strongly on the location in the disk. By averaging the velocity values for all the pixels in radial bins of 200 parsecs, we can generate velocity profiles for all evolutionary phases. So this is what is shown in these two plots for tangential velocities in the top panel and radial velocities in the bottom. The color coding is such that age increases toward lighter colors, the yellow curve being the oldest population. The top plot clearly shows the segregation of the tangential velocity with evolutionary stage, again, sign of the asymmetric drift. The more evolved the population, the shallower is the profile in the center and the lower the overall amplitude. The younger population also seems to show some wiggles in the velocity profile, which could be caused by perturbed kinematics from the bar and the spiral arms. A dispersion profile, the radial velocity profiles, show a dip around 2.5, 3 kiloparsec, which is near the end of the bar, except for the youngest population, which seems to have a strong inward motion at lower radius. Moving on to the structure of the clouds, one of the most prominent features in the outskirts of the two interacting galaxies in general is the formation of a bridge between the two, due to tidal forces stripping gas and stars from the least massive object. The Magellanic Bridge is, of course, well known already in the literature. The bridge is very clearly visible looking at the young population on the left here. It was, in fact, first determined as an overdensity in the H1 gas back in 1963, when we also overplot the vector field of the proper motions from EDR3, the signature of the bridge becomes quite evident also in the old population as a coherent motion of stars from the SMC toward the LMC. Besides the bridge, other structures have been observed in the outskirts of the Magellanic Clouds. For this last analysis, the subset was further cleaned, let's say, to remove even more the contamination, the foreground contamination from the Milky Way. The left plot in the slide shows a star count map of the Magellanic Cloud region, while the right plot shows the velocity dispersion and velocity vector map. Several known features are visible in these maps. The northern and southern tidal arms are seen as an overdensity, a clear overdensity in the left plot, and as a low dispersion feature on the right. The SMC northern overdensity is also visible in the density maps, and there are also some hints of features at ordinate 0, both on the east and the west sides of the large Magellanic Cloud. These appear as faint overdensities, but also appear in the velocity field plot. So these are very interesting and possibly something to look to investigate further in the future. This was my last slide. Of course, I have only shown a selection of the results contained in this paper. And as already mentioned, well, all the papers will be shortly available from the ESA website. I encourage you all to have a good read through. Their precious source of information for anyone wishing to use the Gaia data. And as always, please remember all the work that went into the creation of the Gaia catalogue, and acknowledge Deepak in your work. Thank you.
Thank you, Francesca. That's really good. If you could stop screen sharing now, we'll move on to our next presentation, which is by Floor van Leven, one of the longest serving of the space astrometry community. He's going through probably the most fundamental part of astrometry, going all the way back to Newton's apple and Galileo, is how an orbit is really something falling. So that's over to Floor.
Okay, let's see. Yeah, sure. Does that work, Jerry?
Yep, that's fine. Carry on.
Okay, so we're going to do a little bit of extreme astrometry here. The acceleration of the solar system, something that was not thought to be among our possibilities. Let's see how I get, yeah, there. So it all started with the discovery of stellar aberration in 1727 by James Bradley. He was not looking for that, of course, because he didn't know about it, but they were looking for measuring parallaxes, and they found something that was behaving in exactly the opposite way, in a way perpendicular to the parallax, and it was many times larger, it turned out, than any parallax they were looking for. James Bradley realized that it had to do with the velocity at which we were moving, and therefore had to do with a finite velocity for light coming in, and that's something that was subsequently known as what we say a stellar aberration. And you can see here for alpha Cen an example of how the displacements over the year for the aberration, the red circle and the red ellipse and the blue one here, are actually in perpendicular way. When the aberration is the maximum in a certain direction, the parallax is zero. So it was already speculated in the mid 19th century that if we can measure aberration, if we can measure the change in aberration, that would be measuring a change in the velocity of the solar system. Now, if we look now at the motion of the Earth around beyond that point, then all the apparent positions of all the sources are affected by aberration due to the velocity of the solar system in space. And the two main components of these velocities are the relative to the cosmic microwave background at 600 kilometers per second, which causes an aberration at a maximum of about 412 arc seconds. And there's part of that is due to the rotation of the solar system around the center of the galaxy at about 230 kilometers per second, and that aberration has a maximum of about 158 arc seconds. Now, the second one of these components, the rotation of the solar system around the center of the galaxy, is the one that is changing. The first one, you don't expect to observe any change here. So how much change do we expect over the year? The rotation of the solar system around the galactic center is about 5.6 milliarc seconds per year, which is not very much at all, but that's what we have to work with. We're having 230 kilometers per second and 158 arc seconds aberration. The change in position the maximum change in position that you expect on the sky over the year can be as much as 4.3 micro arc seconds. And that is in the range that Gaia can observe now. So it becomes interesting. So what can we use to measure this? Well, we need extragalactic sources. We need very large distances so that parallax and proper motion can be assumed zero. It's important here that you don't get noise from actual proper motion disturbing this. So we can't use any stars in the galaxy for this, or even in the galactic halo for this, or even as far away as the Magellanic Clouds we can't use for this, because they all have their own parallax and they would all disturb this. So there's a selection of 1.2 million extragalactic AGNs involved in this. A large part of that comes from other surveys, and another large part comes from the Gaia, based on the photometric and the astrometric properties of the sources, which you then can compare with those that we have of known AGNs. The effect then is observed as an apparent proper motion. It's not a real proper motion, it's what looks like a proper motion. The individual measurements of these sources are not accurate enough yet. They may be in the near future, but they're not yet. But as a very large group, they allow for the detection of very specific systematic trends. So the distribution of the AGNs, as we had it available for EDR3, is like this. And of course, you see that within the galactic plane, you can't observe any of them. There's too much obscuration happening there. So you're bound to use those two galactic pole caps. But they offer sufficient information. So we have an expected apparent proper motions based on the galactic models for the expected acceleration can be calculated. The model used here is by Paul Macmillan, which he published in 2017. The people working on this paper have looked at the influence of a whole range of other possible sources that may affect acceleration. And these were all orders of magnitude smaller, and they were not turn out to be significant. So, theoretical, this is how it looks like in galactic coordinates. So you get these points here at the galactic center and the galactic anticenter, and when you look at the galactic poles, the effect is quite large. And when we go then to the observed, and there's barely any difference here. So we get an observed measurement that is very, very close to what was expected on theoretical model of the galaxy that is currently in place. So what is observed numerically? Well, from the Gaia data, we have a maximum proper motion value of 5 microarc second per year, plus or minus 0.35. So it's a 7% accuracy. And that's then equivalent, if you like that more, to 7.3 kilometers per second per million years. Or in real physics, it's 2.32 plus or minus 0.16, 10 to the minus 10 meter per second square. It actually amounts to a change in the velocity of the solar system around the core of the galaxy of 7 millimeters per second on top of the 230 kilometers per second. So it doesn't look much, but it's very important. The direction of the measured change is very close to the direction of the galactic center, as we would hope to see, and you can see that here from the coordinates. And you can see that here in the picture. The big colored blob here is a set of how did they call it, bootstrap resamplings on the data, and the blue crosses here is our set of error bars. The red one here is what has been determined before in VLBI results, and you see that the optical one gets quite a bit close to what we expect to be the galactic center. So all that looks pretty good. So what's still to come? Because of course this is only DR3. For DR4 covering 66 months of data, the relative accuracy could go down to at least 2.6%. And for the final data, if we cover the full 126 months, we could go down to 1%. The final Gaia data therefore has the potential to measure directly the force on the solar system from the galactic gravitational field to 1% accuracy. And I expect there will be further improvements as our understanding of the Gaia data is still evolving, and we're still gaining on what is currently seen as calibration noise. Few acknowledgements. This is all based on a paper that's being published at the moment in the ANA special volume, and a lot of the figures came from Sergej Kleoner at the Lohrmann Observatory in Dresden. Thank you very much.
Thank you very much, Floor. It's good to see that Gaia is actually measuring gravity. You can stop skiing.
Yeah, I'll stop screening.
Okay, so I'll end this science part of, well, we're going to continue with science verification with Georgia, but I'll hand over to Robert Massey. But before I do that, I just remind you what several people have said, is that there's a vast wealth of science coming out of the Gaia data, and there's a vast opportunity for the future. And we, the community doing that, owe everything that we can do to the Gaia DPAC team. So acknowledge and reward and remember and show them your respect. Okay, with that, I'll hand over to Robert Massey, who's going to chair the last part of the session.
Thanks, Jerry. Much appreciated. And it's been very interesting to hear all this, I have to say. So I don't know if new people have joined for this session, but we pitched this last bit as one more aimed at media delegates. So if you're a journalist and you're on this call or in this webinar now, then this is your chance to ask questions. I would offer the usual housekeeping rules. This is use the Q&A box at the bottom right to type in your question. My colleague Lucinda, who's running the RAS account for this, can then bring people in. If there aren't too many, we can offer you audio to ask the questions directly and so on. It just really depends on the number of people on the call. I think that's the main thing I need to brief you about. I should actually say also that if you're following us on Twitter on Royal AstroSoc, we're trying to work in some of our historical material to connect with this. We have things like an edition of Ulugh Beg's star catalogue, as well as the work of Herschel, who was our founding president, just to make a nice connection to today's presentations. And we will make all the materials live from our side at 11 o'clock at the time that the ESA data set goes out as well. So you will certainly be putting that on Twitter. And if you have a look at our website, you'll be able to see that there as well. So I think, though, as I'll be chairing the session, it remains for me to introduce Giorgia Busso, who's from the Institute of Astronomy at the University of Cambridge. And she will be talking about the Gaia data release and the 100 parsec solar neighborhood. So, Giorgia, are you there?
I'm here. Thank you.
Excellent.
So can you see my presentation?
Yes.
Yes, we can, yeah.
So yes, so my name is Giorgia Busso. I'm a member of the Gaia team at the Institute of Astronomy at the University of Cambridge. And I'm here to present you on behalf of the whole Gaia collaboration, the Gaia Early Data Release 3. So yeah, as mentioned, this was more targeted for the media. So I'm going to repeat a few things. So for people that are not familiar with the Gaia mission, just a very short introduction. Gaia was launched in December 2013, so it's actually almost its birthday, and it continuously observe the sky, acquiring data every day, and hopefully will continue to do so until 2024. And is in L2, so it's equilibrium point in the system between the Earth, the Sun, and the Moon, and it moves with the Earth around the Sun. This is important because Gaia uses as a baseline for its measurements the radius of the Earth orbit. What the Gaia does, you heard a lot about this, is measuring the astrometry of the stars, so their distances, their positions, their motion in the sky, but also the photometry, that is their brightness, in particular in three bands. So we have the G band, which is white light, and the two blue and red bands, which are essential for measuring the color and then the temperature of the stars. And finally, the radial velocity that tells us if the stars are moving toward or far from us. And this one of the things that helped allow the Gaia incredible precision was actually the use of the excellent detectors that are made here in the UK by EQV. This was more than 100 detectors. It was the biggest CCD array ever launched in space. And yeah, you heard a lot about this as well. The main goal is making a three-dimensional census of the Milky Way. Here in these photos, figures, you can, it was made combining all the astrometric and the photometric data, and you can really see the details that we achieved so far. So Gaia Early Data Release 3. So first of all, why early? Because this is the early installment of the full Gaia DR3 that will happen in 2022. And what's been the bigger improvement is in the quality of the data, and especially in the astrometry and the photometry. Here in this plot shows the improvement in the number of objects with a better photometry, which is represents from the light blue lines. You can see especially at the faint magnitude that the light blue lines is above the dark blue line, which represent the DR2. So we are doing a lot better in the at the faint end. And yeah, and also, yes, this table shows the numbers of the catalog. So we have more than 1.8 billion of objects with astrometry. So with at least 5 parameters astrometry. So positions, distances, and proper motion. And yes, so the quality of the astrometry. Here, these are two plots, so show the uncertainties of the measurements as a function of the brightness. So on the left, you have the uncertainties of the positions, and all the different lines represent the uncertainty for the different releases. So you can see that going from DR2 to following release, the uncertainty decreases and decreases. Of course, for DR4 and DR5, they are just extrapolated. But just to give you an example on the precision, for instance, if we go at the brightness of 12 magnitude, we go from more or less from 40 to 50 micro arc second. And if you're not familiar with the concept of micro arc second, a micro arc second is the size of a dot at the end of a sentence on a manual that the astronaut of the Apollo mission might have forgotten on the moon, but seen from the Earth. So if, for instance, if this is a page of this manual from the Earth observed with Gaia data, with the Gaia telescope, we would see something like that, only the page and some smudges. And I mean, already we see only the pages. For me is quite amazing. In EDR3, we start to see some more features, and we start to see some images, some kind of line. And so we go on and on with the next releases. Actually, we will be able to read at least some of the sentence, the one in the capital letter. And yes, for the photometry, also here, there has been a huge improvement. Here on the left, you can see the uncertainties of the measurements, again, in fact, as a function of the magnitude. So of course, it increases with a fainter magnitude. But the different, the three plots represent the different photometric bands. And in the darkest line, in every case, represents the EDR3. And you see that in all cases, it's always lower than the previous release. And for the radial velocity catalog is basically the same as in the DR2, only that is much more reliable as so the sources has been matched to the new catalog list, and the wrong velocities have been removed. So it's, as I say, it's much more reliable. And yes, as mentioned, there have been, before to release the catalog, we had to check that we did everything right. And so some studies were carried out to verify that the science we can carry out with the Gaia catalog is good. So one of the studies that was carried out was a look at the stars near the sun. So a sphere centered on the sun with a 100 parsec radius was used to select stars, and the selection was made using machine learning and, of course, based on the good astrometric quantities. And So the results was a catalog, a Gaia catalog of nearby stars with more than 300,000 stars in, as I say, in 100 parsec. To give you some context, the first catalog of nearby stars was published in 91 with a bit less than 4,000 stars in 25 reaching the 25 parsec, so less stars and much smaller. This was updated with the Parcos, reaching higher distances, but still number of objects is quite low, just a bit less than 6,000. What is important with the Gaia catalog nearby stars is the fact that we are able to reach completeness of the stars that we know up to 10% to 100 parsec. So just to give you an idea how much is 100 parsec is around 320 light years. So for the stars we have, as I say, accurate distances and position and motions and colors. So we can actually make a movie. And here, this movie actually was made with the real data. So we can start from the sun, and you can go out, and we start to see the planets that we are going out of the solar system. You see the different colors that represent the real colors of the stars. So red stars are cooler, and blue stars are hotter. We go further and further away to see actually the whole 100 parsec sphere, and then we can start to navigate in this volume. We can pretend to be in a Star Wars movie and go around and see what happens with the stars. We know the motion, so we can see how the stars are going, and based on the motions, we can distinguish a different kind of objects. Here, all the arrows represent the direction and the motions of the stars, and of course, bigger arrows, you see that the objects that are on the forefront have a bigger motion because they are closer to us, while the one in the background, we can see the motion as a smaller arrow. We can look at particular special cases, for instance, of stars that move together, and we can improve our knowledge of binary stars, which are stars that orbit around each other, and as such they actually move together. Here you have an example of this kind of object, and here another example. You see that the motions are the same. And then always based on the accurate motion and position, we can look at other kind of objects. We can look at star clusters. In the solar neighbors, there are two. One is the Hyades, and that you can see here with a different type of stars. And we can select, we can achieve a better, we can select in a better way the members of the clusters based on the motions, because they all move together, because the stars were born on the same gas cloud, so they retain the motion of the cloud, so they move all together. You can see here the members highlighted in yellow and with the same motion. Here there is the other cluster, the Coma Berenice clusters. Also here again highlighted the members and the fact that they move together in the same way. And then we can go out and see there's a big volume, a lot of stars, but how much it is in comparison with actually the whole Milky Way. So we can go out and and see that actually this is just still quite a small fraction in comparison to the whole Milky Way. And yes, I selected just a couple of things. Of course, as I said, we can see we have a deeper knowledge now of this 100 parsec catalog. I just selected a couple of things that were I looked for in the paper. Because I like these things, but there are really many more. So, for instance, the catalog of ultra cool dwarfs was updated. We found, I think it was a bit less than 3,000 new ultra cool dwarfs. These stars are peculiar, if you want, because they are on the boundary between stellar and substellar structures. And one of the most well-known ultra cool dwarf is a TRAPPIST-1, which is became famous in the news because it has a planetary system similar to our own. And yeah, so knowing well this kind of stars can allow us to find new candidates for planet host. The other one is on the other side, let's say, of the spectrum. It's the white dwarf that are actually quite hot, extremely dense object. They are actually at the end, stars that are at the end of their evolutive phase. And here, this plot shows you the number of white dwarfs as a function, the distribution of white dwarfs as a function of their magnitude, and the knowledge of this kind of sequence can give us a lot of information about the star formation rate that happened in the past, and also since these objects are bright not because of nuclear reaction, but because they are only because of their thermal energy, they are slowly cooling down. So we know their distribution in magnitude basically is the distribution in temperature. So we can see, we can model better, we can understand better the cooling mechanism of these objects. And yes, for these stars, of course, we calculate many of the we calculated the orbits of the stars and here there is this nice movie, and we found that most of them, as expected, are moving on the disk in a almost a circular orbit. This movie actually shows you the projection in the future of this motion, and you can see that they go around the Milky Way. And other than that, we also find another thing that we found was evidence of substructures that were associated to streams. For instance, well, the Hyades cluster that I mentioned before showed a tail of stars behind it, and this is a sign of the interaction between the cluster and the galaxy. And the Milky Way. Another thing that was found was a handful of stars that are actually that belongs to the Gaia Enceladus, which was one of the biggest discovery with the Gaia DR2. This the merge. The remains of a dwarf galaxy that merged with the Milky Way about 10 billion of years ago. So we can see all these kind of things. So this was a we looked at the very close stars, but we can look also at the very far objects. As Flor mentioned before, we can look at the quasars, which are actually not stars at all. These are very distant galaxies, and so distant that actually their motion they look almost still, and they can use as a reference frame for the Gaia observation. So what we can see from the motion of the quasars is actually the fact is the reflection of our motion in in the Milky Way. Here, this video show better this effect. And well, so we have a catalog 1.6 million of quasars, which is quite big, quite accurate. You see all the arrow points on the same direction, and this is actually caused by the acceleration of the solar system. This was the first time. Well, this was again was possible only with Gaia early data release 3, because the precision of the measurements increased hugely, and the value so the value of the acceleration of the solar system is this one, is 7.3 kilometers per second per million of years, and is known with a precision of the 10%. And this is the first time we can measure so precisely the acceleration of the solar system in the visible range. And the other things was a look at how Gaia can perform in extreme circumstances, if you want. So looking at the stars in external galaxies. So for instance, the Gaia Magellanic Clouds, which are these dwarf galaxies that orbit around the Milky Way. And looking at the proper motions of the stars in these two galaxies, especially in the Large Magellanic Cloud, we can trace we can see how the stars move, we can see which kind of stars are, because we can distinguish between young and old population. So we can trace the difference in the kinematics of the different population. And for the first time, we can map the velocity component for multiple stellar evolutionary phase in a galactic disk that is outside the Milky Way. And of course, we also looked at the Magellanic Bridge that connects the two galaxies, and we confirmed that yeah, it's made of young and old stars moving from the small to the large Magellanic Cloud. So so far, Gaia had a huge impact. Gaia is the most queried archive, and thanks to that, we have more than 3,600 referred papers, and yeah, it's been a revolution in many fields of astrophysics, from galactic dynamics to stellar evolution, but also for close by objects, like for instance asteroids in our solar system. So for sure, Gaia EDR3 will bring new exciting discoveries that will help us understand better our place in the universe. And yeah, I just wanted to say thanks to all the members of the ESA Gaia DPAC that worked very hard in the past months to allow the release of this data. A lot of members of DPAC actually are in UK, so I wanted to mention the people, the team in Edinburgh and Leicester that were crucial in the improvement of the astrometry. The team in Cambridge, which I'm a member of, that yeah, is responsible for the photometric processing of the Gaia data, and the team at UCL, which is responsible for the Gaia radial velocity catalog. And yeah, again, some acknowledgement here. Yeah, the Gaia, I leave it here. So the Gaia videos were made based on these three paper with the Gaia Sky, which is a software available to everyone. And of course, if you want more information, go on the Gaia ESA webpage, probably now. And yeah, that's it on my side. Thank you for being here.
Okay, thank you, Giorgio. I think now we're going to invite all the, if you could stop sharing your screen, and we'll now invite everybody to switch their cameras on if they're one of our panelists. We do have a few questions that have come in. I'm going to ask my colleague Lucinda to help with some of this. One of the first ones we had was from Schilling, who I know is a a freelance journalist in the Netherlands. So Hovert, are you there?
Yes, I'm here.
Excellent. Go ahead.
Actually, my question was already answered by a couple of earlier presenters. I was wondering about the completeness of this catalog within 100 parsec. How many red or white dwarfs might we be missing? So how complete is this census of over 300,000?
Do you want to take that one to begin with?
Yes, well, I think it's a very complete. I mean, I didn't show in the presentation, but we can build the luminosity function of the whole catalog, and we go from the very bright star to the very faint one. And yeah, it's as I say, I would say more or less 100% complete. We can see everything. I think. Somebody confirm this, please.
Anybody else want to come in on that?
I think it depends a bit on the kind of star. So if you're looking at normal main sequence stars, yeah, it's pretty near 100%. Yeah. When you're looking at fainter objects like white dwarfs, we do start to lose the very coolest ones when we get out to 100 parsecs, but it's still better than 80%. I mean, the completeness is just incredible.
Thank you, Martin.
Yeah.
Okay. Oh, sorry. Was that Nick? I heard.
Yeah, I was just going to say there's some sort of the details are in the paper. I suppose it falls off pretty quickly with later type stars, but as Martin says, it's pretty good.
Excellent. Okay. All right. The next one. I know during your talk, Georgia, Victoria Allen had her hand up, and then I just prompted Victoria, if you're there, we'll switch on your mic, and if you've got a question to ask, go right ahead. You could say where you're from as well.
Hi there, I'm from the Daily Mail. I just wanted to ask if there was anything kind of interesting that had been thrown up that perhaps told us something we didn't know before, or suggested that there was some kind of received wisdom about stars which people think but is now wrong. I also wondered if I could get the absolute increase in the number of stars we now know from the last time that something like this was done.
Okay, who'd like to take that? Georgia, do you want to start?
I didn't hear well the question.
I can repeat some of it, but it might need Victoria to do the same again. But it was just partly about asking about sort of maybe key discoveries that have come out of this, and also what the increase in the number of stars is for which we have these positions in this data set compared with the past.
Well, it's a huge, well, for the Gaia catalog of nearby stars, it's a huge improvement. I mean, it's we go from what was less than 6,000 to more than 300,000. So it's I would say it's really a big improvement, and it's not only that we know that there are more stars, but we know very accurately their positions and their motions in space, and so it's huge. I would say that this really allows better knowledge of where we are in space, of our neighborhood, if you want. We get to know better our neighborhood. Yeah.
Yes, but sorry, I thought you said that less than 6,000 was in 1991. So I just wondered if there'd been anything subsequently that had added to that number.
They were added. So yeah, well, the catalog was updated in well, the catalog was first released in 91 with less than around 3,000 stars.
Right.
Updated with other observation in 98 with the Parcos, with another satellite, and that observed a bit further away, reached 100 parsec, but it wasn't powerful enough to observe also the fainter stars. While Gaia is, we can see much better the fainter stars.
Thank you.
We're talking about the nearby stars in those numbers, and that's gone up to 300,000. And we just did not have the data to say that those stars were in the solar neighborhood before. So it's a massive increase in our knowledge of this region of the of the galaxy. But if you're talking about the total number of stars in the galaxy, that's very much larger.
Yeah, Gaia, I mean, for instance, the Gaia catalog is almost 2 billion of objects, but it's only about 1% of the total number of stars of the whole galaxy. So
it's probably worth noting. I mean, in before 2016, we knew sort of good distances for about 100,000 stars, and then when we put out our first Gaia catalog, we had photometry or brightnesses for about 1 billion. In 2018, we put out our catalog and we had 1.7 billion stars where we were with good precisions on the distances, if you like. And now we're putting out a catalog with 1.8 billion objects. So we're getting more, but the accuracy of the data points has gone up by a factor of 2 for proper motions, for instance. So when we're measuring the motions of objects, we're now getting on for 2 billion with factors of 2 better than what we put out a couple of years ago.
Sorry, just one follow-up if I could. When you talk about nearby stars, what do you mean by that?
The nearby star set that we were talking about, the 100 parsec, that's within a few hundred light years. But Gaia now measures basically stars all the way through our Milky Way and beyond to the Magellanic Clouds, which are more at sort of 50,000 parsecs. 50 kiloparsecs.
Okay, I'm going to move on to Jonathan Amos from the BBC, who I can see has typed in a good number of questions. Are you there, Jonathan? Is your audio on?
Unmute. I think I'm unmuted. Can you hear me?
We can hear you now.
Yeah. Some of you have answered the questions. I think I just sent one to George about his uncertainty level. I don't know if he's typing that up. My connection dipped out at that moment. I know Georgia gave one uncertainty measurement, but George, I think you gave one. A coin at 200,000 kilometers, I think it was. And was that a 15th magnitude star source, was it?
Hi, Jonathan, it's Nick Rowell here. I think you're referring to my talk. Yes,
was it yours, Nick? Apologies.
Yeah, no problem. Yeah, that was for a 15th magnitude star, and the uncertainty on the parallax is equivalent to a pound coin viewed at around 200,000 kilometers.
And in micro-arc seconds, that's what?
In micro-arc seconds, that's 0.027.
Right, and how does that compare to the pre-launch expectation specification requirement? I mean, how good are we? How good is Gaia compared to the brochure?
Good question. Maybe one of the longer serving members of the consortium involved in that might be able to answer.
Loaded question, isn't it? How good is Gaia? Maybe Jerry Gilmore or Floor might want to answer this one.
Yeah, let me comment briefly. Is that famously, of course, there is a residual uncertainty that is coming down very slowly on the precision, i.e. the 0-point accuracy of the Gaia results. But the formal accuracy is now very close to design specification. And that's largely because of the benefit of a very benign sun. So the detector performance has been better than predicted all the way through, and that is compensated for a few other challenges that came up early on. So the predicted performance for the data that we currently have in hand that will be published in data release number 4 will be very close to that predicted for the original lifetime of the mission, with the possible exception of the 0-point uncertainty, which of course is key because it's the Hubble constant and all the rest of it. And that's, there's a whole paper describing how that's being improved, but will eventually get down to the specification. There are enough secondary calibrations being put in place, but that might take even a bit longer before we get to that level of precision. But for everything else, The total number of stars is roughly twice the conservative estimate we had originally, and that's because of the detectors working so well. The photometric precision from the Cambridge team is already as good as was hoped. The radial velocity precision is going to be even better, actually, in spite of its challenges. It's amazing. And the astrometric precision will be close to that predicted. And then because of the extended mission, it will end up more than twice as good as expected.
Right. So in terms of radial velocities, because there was a lot of debate immediately after Gaia had launched, or around the time that Gaia had launched, that we wouldn't get as many radial velocities as we would have liked. You're saying that actually that's not the case now.
Yeah, well, Mark Crobber might want to add a bit to this, but no, fundamentally, people were able to fine-tune the onboard selection system in such a way as to compensate for the extra background that came from the scattered light, and the extended mission gives more data. And so the combination of those two is that the radial velocity harvest, as you might call it, the number of good velocities at the end of the mission, plus the number of good spectra, will be near enough what we originally hoped for.
Great. And can I just finally, Robert, just sorry to do this to you, but we are journalists, and can somebody give us our top quote for our publications? You know, I mean, sell Gaia to us, sell it to the public. You know, you've given great presentations, but come on, sell it to us. Why should we care about this discovery machine in space?
Gaia data is like a tsunami rolling through astrophysics. It touches every part of astrophysics, from nearby stars, the planets in our solar system, all the way through to the edge of the universe. As Jerry said, those 1,600 papers are the largest number of papers published based on data from any observatory in the world, or in the solar system, if you want to take it like that. It's just transformational. You'll be talking about astronomy before Gaia and after Gaia. And those two things will be completely unrecognizable when you compare them.
Anybody else want to have a go?
Yeah, I was going to say, any other sales?
Yeah, I think it's the fundamental nature of this mission that gives it the huge impact. Yeah, it does something. It strengthens the foundation on which astronomy is built, and as a result of that, everything in astronomy becomes better in many ways. Yeah, everything becomes better defined because the foundation has improved significantly, very significantly.
Sounds fair. Okay. Those are two nice pitches. They're good enough for you, Jonathan, or is it not you we need to convince?
Fantastic. Yeah.
Well, another way of looking at it, I mean, basically Gaia tells us everything, or a large chunk of knowledge about the Milky Way in terms of characterizing every star in our Milky Way, or a large percentage. So it's the same sort of thing as you're, you know, trying to understand the human body. You want to type all the cells, and that tells you, you know, you can probe how cancers evolve, for instance, and these sort of things, and you know how life goes. Well, it's the same story with Gaia and the Milky Way. We can now type, getting on for a few % of all the stars in our galaxy, and not only do we know where they are moving, where they've come from, where they're going, but we know where they were born, how they were born. We know about their chemical makeup and so forth. So it really gives us an insight into how the Milky Way lives in that respect, and I think that's the really crucial bit at a global level. I mean, we're not sampling small numbers. We're not talking about a few stars here. We're talking about, you know, billions of stars, which gives us the ability to really probe at a meaningful level the whole population of the Milky Way. And that's, you know, similar to the sort of way you want to do with studying people, if you like. It's like knowing, you know, what everybody is up to in the UK. If everyone's got a tracker, we can tell you, you know, whether they're sweating or not. And it's a bit like that with the stars here. We can tell you which ones are sweating, which ones are active, which ones are dormant, which ones are going to die, which ones are going to explode. And I think that's the bit that Gaia really gives you. And it means that other missions can then build on that. They can go in and focus in on, you know, the details, if you like. But Gaia gives you the big picture, it gives you the map, and it tells you where you've got to go.
There's another short quote.
A short sales pitch.
Yeah, short sales pitch could be that there is hardly a field of astronomy that isn't revolutionized by the Gaia data.
Okay, that's a nice point to end in the response to that question, I think. So, because I have a couple of others coming in at least. So we've got Megan Gannon from space.com. Lucinda, if you're able to bring her in. There we go. You should be on now, Megan.
Okay, great. Yeah, so hopefully building on this discussion of the impact of Gaia, I was hoping you could talk a little more about the scientific implications of these new measurements of the acceleration of the solar system. So maybe in other words, could you give some examples of questions you're excited for scientists to ask using this improved data set or this new data set?
Who
would like to take that?
Okay, let me. Here we go. I mean, the really interesting thing about the first measurement of how the solar system is falling towards the center of gravity, just like Newton's apple fell on his head and he realized that the moon was falling to the center of the Earth, is that it gives you a way to do precision measurement. Now, the immediate conclusion from the current acceleration, is the technical term, the motion of the sun, is that roughly half of the weight, the mass interior to the sun, that holds our sun in our Milky Way, is stars and gas, and the other half is this mysterious dark matter. So even our own sun is moving so fast that our whole Milky Way would fly apart if it wasn't held together by the dark matter. That we've got no idea what the dark matter is. The hope is that by continuing experiments along the line that we're doing and making them more precise and doing them on different scales, we'll be able to see if there are different types of dark matter. Is there some dark matter that's associated with the disk of the Milky Way and a different sort of dark matter that's associated with the halo of the Milky Way? Is there some sort of dark matter that's in great big blobs that don't have any stars in them? And these are sort of moving through, or are they not there? If they're not there, that's telling us something too. And so these precision tests of the way mass is distributed and the way things are moving around are actually probing the limits of fundamental physics. This is the mysterious theory of everything that we haven't got and we don't know how to get to. All we know is that there are puzzles, all of which are coming from astronomy, which are not explicable by our current physics. And so we have to do the experiments to say, tell us more.
Thank you, Jerry. Anybody else want to add anything to that?
Yeah, I think some of the things that is interesting to note. Some of the things we're happy to see that we've measured an acceleration of the solar system towards the galactic center. We would be somewhat worried if it was not towards the galactic center. So at least we don't have to rethink all of our understanding of how the Milky Way is.
Thank you. Okay, I'm just looking through the list. Probably coming towards the end of our time, but are there any other final questions that anybody wants to pitch? Otherwise, we can bring it to a close. I can see a hand. I think I can see. Is that a hand up from Jonathan again? I think it is. Let's bring Jonathan in again, assuming. Oh, and also Jonathan O'Callaghan. Yeah, I saw your question earlier. Let's go to Jonathan O'Callaghan first, if that's okay. Thanks, Lucinda. Great, thank you. Go for it, Jonathan. You should be on now.
Hey, can you hear me okay?
Yes, we can.
Great. Yeah, I just wanted to clarify for my simple scientific brain why there is this, the reason for the early release and why there weren't similar early releases before the first two Gaia releases. What is it exactly about this release that necessitates this kind of release before the full release in 2022?
Okay, shall I answer that one?
Sure.
Yeah. So the processing of the Gaia data is effectively in two stages. First is the stuff that we've just presented here. That's the basic astrometry and the photometry. And the second stage is the interpretation. It's the analysis of those data, the variability, the astrophysical parameters, double stars, solar system objects, and so on. And it was considered that the time lag between us getting ready the photometry and the astrometry, and before everything would be ready, would be too long, and it would not be good for the scientific community for us to sit on those astrometric and photometric data for, say, another 1.5 to 2 years before releasing them. So it was decided to release those data early, and then release the second part, which provides a lot of the analysis of those data as the final part in early 2022. It's the complex nature of this data that led to this.
Right. Okay. And with the first two releases, that data just all came kind of at once?
At the first two releases, there was far less of this analysis data involved. So there were much smaller volumes of data being analyzed. So there was not that large delay anymore. Not yet, as we have already in this release.
I think it's also a question of number of products. So different,
all different
so
products
that require different validation analysis. You see.
Okay, thank you.
Sorry, I'm unmute myself as well. We've got another one hand up from Jonathan Amos again, if you want to come back with something.
Good, thanks. Yeah, there aren't enough Jonathans in the world. There's definitely a question for George. So you've removed some of these crazy stars moving at 600 kilometers per second. But if I read your graph correctly, there are still stars moving towards us and away from us at about 500 kilometers per second. I mean, is the thinking that these may be interlopers, that they don't belong in the Milky Way?
Yeah, so thanks for your question, Jonathan. No, so previous surveys have found radio velocities that go this quickly. So out to plus or minus 500 kilometers per second has been seen before. And these are often halo stars. So stars that often spend most of their time away from the galactic disk, and then you see them plunging through. But some of them could be interlopers. They're just not as extreme as the ones that we've had to remove.
Okay.
So yeah, a full analysis of them with the astrometry as well should be able to pin down their origin. Does that answer your question?
Yeah, perfect.
Yeah.
Excellent.
Combination of velocities and orbits and directions.
Okay. All right. Well, we can bring this to a close in a second, I think. Do any of the panelists have any final words? And then we'll end the briefing. I should actually add for everybody, including panelists, that because of the nature of this, because we're recording it and we'll put it on YouTube and all the rest of it, it will be quite an abrupt end. So there's sort of no opportunity for informal chat afterwards. But if there's anything else anybody wants to close with, then now is your chance.
I would expect the first papers from this data release probably already hitting APH.
Great, and of course the data should now be live, right?
The data will now be live. That's correct.
If you're a journalist, you have the release. So I think
a lot of the astronomers will have left this this broadcast to go and work on the data already.
I think a lot of the astronomers will. That's
yeah. I mean, it is data that actually arrives on schedule, which is also good for the community, that this has not been hit by any pandemics or so, that we can put the data out and the research community can benefit. This has been a lot of fun.
So the scientific papers are already out on A&A.
Right. Excellent.
The next question will be, how many astronomers does it take to crash the Gaia database?
Let's find out. Yeah, maybe it'll be more reliable than the tier location one in the UK. But all right. Well, thank you, everybody, particularly our panelists, for spending time today, and for everybody who's joined, and members of the media and the UK and wider astronomical community, actually, for connecting to this webinar. We will feature some of the things on our YouTube channel, the Royal Astronomical Society one. We will put some of the stuff on our Twitter account as well. Some of these files are huge, I should stress, so it's not quite as easy to do that as you might imagine, but they really are fantastic. If you want to see things like the remarkable videos that Georgia presented, we'll make sure those are available. And I know that I think there'll be material on the ESA website and in other agencies around the world as well. But with that, I just want to say thank you to everybody, and I think we should end it there. And thank you, and we look forward to seeing some nice stories written up about this as well.
Yes. Thank you, Robert.
Thank you.